Okay, so today I want to explain the process of electrolysis and how you make alkaline water, or some people call it ionized water. And I hope to explain why the term ionized water or alkaline water is actually a misnomer, and hopefully you'll understand better how your machine works. So first off, let's just talk about water. So what is the molecular formula for water? We all know that it is H2O, 2 hydrogens and 1 oxygen. And if we draw the structure of water, we know it looks like Mickey Mouse, right? Hydrogens out here like that. But why is the water molecule bent like this? Actually, the bond angle is about 104.5 degrees. Why is it like that? And it turns out it's because there are electrons right here. We call these lone pair of electrons. Now, don't get too confused here. I point that out because I'm going to explain to you what's called the self-ionization of water, or autoprotolysis. So water exists in equilibrium. There's water, basically you have 2 water molecules are converted into this little guy right here. This is acid, this is hydronium, the hydronium ion, and the hydroxide ion. Okay, this is the acid, this is the base. You can kind of think of it like that. And I'm explaining how this happens with water. Okay, so let's draw another water molecule right here. Now this water molecule, and we have this water molecule, and of course in our glass this is surrounded by lots of other water molecules. Let's say we have one just sitting right here as well. Okay. Now, remember, there's electrons right here, right here, right here, right here, right here, right here. Okay? These electrons make the oxygen have a partial negative charge, and the hydrogens right here have a partial positive charge. Does that make sense so far? Now, we all know that negatives and positives attract. So basically what happens is the electrons from here basically pull on this hydrogen right here, and so we're removing that hydrogen and making the electrons stay onto the oxygen. So let's imagine what would that look like if this hydrogen came onto this one and this was left alone. Let's draw that now. We would have this molecule here, and it would be a negative charge now, and we would also have this molecule here, which would be a positive. That's positive and this one's negative. Well, look, see the resemblance? This is the acid, hydronium, and this is the OH minus, hydroxide. Does that make sense? This always happens in water, and it's actually given a name for this. Is called, that self-ionization of water has a constant. It's the Kw, the ionic product of water, basically. And this always happens in solution. In fact, we could even give the number. It's 1 times 10 to the negative 14. Okay? Now, we don't need to go into more math and derivations, but now you're going to start understanding how electrolysis it works. But first let's talk about ionized water. What does that mean? Well, like I said, I drew right here water. Okay, let's just draw another one. We have this water molecule right here. Okay, this is a neutral water molecule. An ion, as we know, is an atom or a group of atoms that has an electrical charge, whether it be positive or negative. Well, see this water molecule here? There's no charge on it. It's neutral. And so when somebody says ionized water, that suggests that somehow or the other you have a water molecule that either has a net negative charge, meaning it somehow has gained another electron or something, or a water molecule that has a net positive charge, meaning it's somehow lost an electron. Now, although these types of species may exist in bulk water or different, physical chemistry type things. They're very unstable and highly reactive. This would suggest a solvated electron. That's not what's going on with our drinking water. Okay, so just to eliminate confusion, the idea or the concept of having ionized water in the absolute sense would be indicative of something like this. Guys, that's not what's going on. That's not what's happening. So now let's talk about how you make alkaline water, how this electrolysis works, okay? And first let's talk about pH to help you understand this a little bit. Let's go back up to this formula right here. pH stands for the potential of hydrogen, but really the P is a symbol which means the negative log of something, and so the negative log of the hydronium ion concentration. So what we see right here, we have these two are always in equilibrium, and in fact this one right here it has 1 times 10 to the negative 7, and this one is 1 times 10 to the negative 7 also. Of course, these two multiplied together would give us the 1 times negative 14, but these are both at equilibrium. And so if we take the pH, right, which is the negative log of the hydrogen of the acid, the negative log of 1 times 10 to the negative 7 equals 7. And that is why neutral water has a pH of 7. Okay? Now, what would happen if we increased a whole bunch of this? Then you would have more acid, right? Therefore, the pH would be a lot lower. And this, by default, you would have a lot less of the hydroxide ion. Okay? So let's talk about now how electrolysis works. Keep this in mind, as you'll see it comes in useful when we talk about how the machine makes the water alkaline. Okay? Now electrolysis, of course, has been used for a long time, decades, to produce hydrogen gas. Okay? So again, let's just draw our water molecule right here. And for simplicity's sake, let's say that this dissociates into the proton and the hydroxide ion. Remember, this actually does not exist. It's in the hydronium form, which is the HO3+. But for simplicity's sake, we're just going to leave it as H+, okay? Now let's talk about the electrodes of the electrolysis. So right here are our electrodes, okay? And let's say that this one right here is negative and this one is positive. So this is for an electrolysis, this is called the cathode, and this is the anode. It's different for like a battery, but in electrolysis, the cathode is negative. Okay? Now remember, we have these two things float in solution. We have some protons, we have some hydroxides. Okay? So what happens? We turn the power on, you push 9.5 or whatever, what's going on? Well, these protons are going to be attracted to the negative side of this cathode, right? And so basically, let's come over here, let's draw what that would look like. We have a proton right here, and let's say that we have another proton right here. They're attracted, and this is negative, right, because electrons are coming off. Electrons are going into the water. These electrons then combine with these protons right here, okay, and you make atomic hydrogen, okay. These guys then form the neutral atomic hydrogen, okay. This has been termed as active hydrogen. Now, that's actually incorrect. It should be reactive hydrogen. It is a free radical because it's missing a lone pair of electrons, and because it's a radical like that, they actually react together to form diatomic molecular hydrogen gas. Okay, H2 gas. Okay, so the idea of having active hydrogen in the water stems from the idea you have this free radical thing that somehow stabilizes the solution. Not true. So like I said, these two react together to form the diatomic molecular hydrogen gas. So the idea that there's active hydrogen or reactive hydrogen in the water, it's simply not the case. It's not true. There's hydrogen gas. And this hydrogen gas is when you make your water, you see all these bubbles in there and it's kind of foggy. That is hydrogen gas. That is what is therapeutic. Okay, that is what's giving you all the benefits of the water. But now let's go to pH really quick. Okay, remember pH was the concentration of this guy, right? The concentration. The more of these protons we have in the water, the lower the pH. Okay, but what do we just do? We took these protons and we turned them into hydrogen gas. Therefore, we effectively decreased the amount of protons in the water by making hydrogen gas, which means now we have more of these. So the hydroxide concentration goes up, the proton concentration goes down. And that is why you have an alkaline pH. Your pH from, 9 to 10 to 12, whatever it is just indicative of less of these guys, which means more of those guys. And so generally speaking, the higher the pH, that would mean the more hydrogen gas was produced. And of course, the more hydrogen gas that's in your water, the better for you. Because hydrogen gas, again, is the therapeutic molecule. And I'll talk about that in a little bit of why hydrogen gas is so good. In 2007, there was an article published in the Journal of Nature Medicine that showed that molecular hydrogen gas can selectively scavenge only the cytotoxic free radicals. This was a groundbreaking article because it was published in one of the most prestigious and respected scientific peer-reviewed journals with an impact factor greater than 20. This created great excitement in the scientific and medical communities, and now hundreds of other studies have been published showing that hydrogen gas can also effectively upregulate the body's own antioxidant systems, such as superoxide dismutase, glutathione, peroxidase, and catalase. It is no wonder that remarkable therapeutic effects have been observed in a wide range of diseases.